Hi everybody. In this video I'm going to do an example projectile motion problem. Imagine we have a projectile launched from some unknown height above the ground. Imagine this projectile is given an initial velocity that has a magnitude of 12 meters per second and a direction of 60 degrees above the horizontal. Imagine that the ball goes through its parabolic trajectory and then impacts the ground 3 seconds after launch. Given this information, we're asked to calculate A, how far does the ball travel horizontally while in flight? That is, let's calculate the horizontal component of the ball's displacement while it's in flight. Part B, from how high above the level ground was the ball released? Part C, find the magnitude and direction of the ball's impact velocity when it hits the ground. Impact velocity can be thought of the velocity the ball would have had at this point if you, instead of having ground there, had a little blank spot. So you can also think of it as the velocity it has just the instant before it hits the ground. Great. All right, so let's get started. It turns out we can solve these parts in order. It also turns out that we could solve them in different orders. And I'll have some comments about that at the end. But the first thing we need to do is take our given information and break it into components. Now, it's convenient in a projectile motion problem to take the x component to be in the plane of the projectile, parallel to the ground, and the vertical component to be upward, the vertical direction to be upward. So x horizontal, y and vertical. Now, we know that projectiles, in the absence of air resistance, and we're going to ignore air resistance in this problem, the magnitude of these velocities are small enough, that the acceleration of a projectile near the surface of the Earth has a magnitude of 9.8 meters per second and a direction downward. In a coordinate system where we're taking x to be horizontal and y to be vertical, the x component of the acceleration will be 0, and the y component of the acceleration will be negative 9.8 meters per second. Negative because down is opposite the positive y direction. Okay, great. So let's get started. Let's start by finding the horizontal and vertical components of this velocity at launch. To find the horizontal component of this velocity, well, I can sketch this in. There's the horizontal component. There's the vertical component. These make a right triangle. So this side and this side, I could take this side and put it over here. And then I have a right triangle with a 60-degree angle here. So this side here is adjacent to the 60-degree angle. So for the x component, we're going to have v sub x 0. And I'm going to use the 0 subscript because I'm going to set my time equal to 0 at launch. Then, at impact, my time will be 3 seconds. So v sub x at time 0, or v sub x 0, that will be 12.0 meters per second times the cosine of 60 degrees. Cosine of 60 degrees is a half, so this works out to 6.00 meters per second. Great. So at launch, this projectile has a horizontal velocity component of 6 meters per second. Now, since the horizontal acceleration component is 0, that's the horizontal velocity component that this projectile will have through its entire flight. So if we were to shine light from above and watch the shadow of the ball along the ground, the shadow of the ball along the ground would travel at 6 meters per second. All right, let's get the y component of the velocity. I'll write that. I don't really have enough room over here. I'm going to write that right here. V sub y 0. Now, this side here is really sitting right there. This side here is the opposite side of the 60-degree angle. Opposite goes with sine, so I've got 12.0 meters per second times the sine of 60 degrees. And that works out to 10.39 meters per second. Now, this is in the positive x direction that we chose. This is in the positive y direction that we chose. So both of these come out positive. All right, so let's continue. Now, we've got these x and y components of the initial velocity. Let's see what we can do with this information. So we'll take these questions in order. It turns out we can. Part A, how far does the ball travel horizontally while in flight? Well, what we want to do then is look at the change in x, delta x. Now I've written out our equations for a constant acceleration component in terms of y right here, but we could also write those in terms of x. So if I have a constant a sub y, then delta y is equal to v sub y 0 times t plus 1/2 times the y component of the acceleration times the elapsed time squared. I could write a similar equation for x. Let's do that right here. So delta x equals v sub x 0 times t plus 1/2 times a sub x t squared. But the x component of the acceleration is 0. So we can just take this information, plug in. The x component of the velocity at time 0 was this 6.0 meters per second. So I've plugged that in for this. And then for the time, well, if I want to know how far horizontally it goes in the time from launch to impact, then I want the time from launch to impact, which is 3 seconds. All right, 6 meters per second times 3 seconds gives us 18 meters. And that is the answer to part A. I'll even write it right here. How far does the ball travel horizontally while in flight? It travels 18 meters. Horizontally. All right. So now let's look at the next part. From how high above the ground was the ball released? Well, that's a question about the y component. Now, we can't get at this necessarily directly, but we can get at it almost directly. What we can calculate is the change in the y coordinate while the ball is in flight. The ball is in flight for 3 seconds from launch to impact. During that 3 seconds, the ball goes up and comes down. That's just looking at its y component motion. So the net effect during this 3 seconds, going up and coming down, is just to go from here to there. So what we want to find is the y component of the displacement during this 3 seconds. That'll be from here to here. The amount of that will basically be the height above the ground that the ball was launched from. So let's calculate that, and let's put it right here. All right, so this is a question about delta y. We're going to try to find the displacement from here to here. In fact, I'll sketch that out. So what I want to do is find this. This is what we're going to find along the way to getting what we want. We get this delta y during 3 seconds. So we'll have v sub y at time 0 times the elapsed time plus 1/2 times the y component of the acceleration times the elapsed time squared. If we put in the time from launch to impact, the 3 seconds, that'll give us this downward displacement in 3 seconds. All right, so let's plug in delta y equals, well, v sub y 0 was 10.39 meters per second. The elapsed time, that's 3 seconds. Plug that in, plus 1/2. A sub y, that's our negative 9.8 meters per second. We took up to be the positive y direction, so this downward acceleration, it's in the negative y direction. So minus 9.80 meters per second. And then I'll put in my 3 seconds. I've got to square that. Look at our units. Meters per second times seconds will give us meters here. Meters per second times seconds squared, right? 3 squared times seconds squared. The second squares will cancel. We end up with meters here. Now, if we hadn't had this downward acceleration, the displacement would have been upward. The thing would have just kept traveling upward, and it would have traveled, over 30 meters upward in the 3 seconds. But it has this acceleration, and that ends up having an overall downward displacement. So let's do that calculation. I've already punched that into my calculator before, and I get negative 12.90 meters. Now, I've got to be careful. We haven't calculated the answer yet. What this tells us is that the displacement was 12.9 meters downward during the 3 seconds. What this really tells us is the impact is 12.90 meters below the release point. What that tells us then is that the ball was released 12.9 meters above the ground. So, ball was released from 12.9, I'm going to round this now, meters above the ground. And that's our answer. So, from 12.9 meters above the ground. Fantastic. That's the second part. Notice we could have solved the second part before we did this part. These two parts were independent. Once we had this information, we could have solved these in either order. All right, last part. Find the magnitude and direction of the ball's impact velocity vector. Well, to get the magnitude and direction of this impact velocity vector, magnitude, proportional to the length of this arrow, direction, some number of degrees below the horizontal, we're going to first need to find the horizontal and vertical components of the impact velocity vector. That is, we need to know the x component of the velocity 3 seconds after launch and the y component of the velocity 3 seconds after launch. Well, one of those we already know. We already know that the x component of the velocity 3 seconds after launch is 6 meters per second. Why? Because the x component of motion has no acceleration. If there's no acceleration in a particular component of motion, that means the velocity in that direction isn't changing. So v sub x final is equal to 6.00 meters per second. The horizontal component of the velocity is constant from the instant the ball leaves the hand until the instant the ball hits the ground. The y component of the velocity we've got to do a little bit more work for. I'm running out of space down here, so let's put this up here. So I'm just put a little asterisk here, and then asterisk here, so to know that we've gone up to there to do the calculation. All right, so let's use our y component of the velocity expression. The y component of the velocity will be the y component of the velocity at time 0 plus the y component of the acceleration times the elapsed time, or in other words, the y component of the velocity at time t will be the y component of the velocity at time 0, plus however much the y component of the velocity changes due to the y component of the acceleration during the elapsed time t. We can always write this if a sub y is constant. For this projectile motion problem, with our coordinate system chosen, a sub y is negative 9.8 meters per second. So we can take this, past y velocity into a future y velocity using this expression. So here we go. Let's plug in. V sub y will be equal to V sub y 0, the 10.39 meters per second. That goes in as positive because this y component of the velocity at time 0 was upward. Then plus a sub y, that's a negative 9.80 meters per second times the elapsed time t of 3 seconds. That's 3 seconds from the time the thing had this velocity till the time we want at impact. Y component of the velocity, I should say. Okay, great. So we can work out that number. I've already done that calculation. You can check the calculation in your calculator. And I get negative 19.01 meters per second, which we should probably round to just 19.0, but I'll do the rounding after we calculate the magnitude and direction. Okay, great. So now this, I just wrote v sub y here, and here I wrote v sub y final because I'm saying, oh, my final, final instant is at impact. That's 3 seconds after, but this is the same thing. This could be any final y component at any time. I plugged in 3 seconds, so this is actually what we've calculated here. So I'll just note that this was a little arrow there that we calculated it, minus 19.01 meters per second. Great. So now we have the x component of the impact velocity, the y component of the impact velocity. Those have a right triangle relationship. I can take this, put it over here, and so I'd have a right triangle like this. So this is the adjacent side. This is the opposite side. I mean, I've written it here, but it could go right there. So we can find the hypotenuse side, or the magnitude. I'll do that calculation up here as well. I'll change pen. So I'm just going to do impact velocity calculation. All right, so v final, the magnitude of the v final vector will be the sums of the squares of the final x and y velocity components. So I can take the 6 meters per second, plug in here, take the negative 19.01 meters per second, plug in here, square both of those, take the square root, and I get 19.9 meters per second. To get this angle below the horizontal, remember again, I've got a right triangle here and here. So this side is adjacent and this side is opposite. This side is really this side. So tangent of theta will be opposite over adjacent. So theta will be the inverse tangent of opposite over adjacent. And I'm putting that in absolute values to force the angle to come out positive, because then I can have this positive angle and I can say that's some number of degrees below the horizontal. Now let's plug in for those. So theta will be the inverse tangent of negative 19.01 meters per second divided by 6.00 meters per second, all in a square root, all in absolute values. So we take the absolute values there, it makes the whole thing positive. Then we take the inverse tangent, making sure our calculator is in degree mode. Meters per second divided by meters per second gives you no units. So inside the argument of your inverse trigonometric function, you shouldn't have any units. All right, and let's grind out that calculation. That comes out to 72.5 degrees. Okay, and what is that? That's below the horizontal. Below the horizontal. Okay, so we can now finally express our impact velocity vector, v final vector, in terms of a magnitude and direction. Let's do that. I'll change the pen color. That will be 19.9 meters per second in the direction 72.5 degrees below the horizontal. And we'll box that up. And that was our answer to part C. All right, so we've solved it all. We could have done these in different order, right? Once we got this information, then having the time from launch to impact means we could, use any of these equations, at any time. So We could have done all of this first, or we could have done this first. Instead, we chose to do this first, then we chose to do this, then we chose to do this. It turned out that we could do everything in the order we were asked to do it. But if you're given a problem and you get stuck, try doing a different part first. Maybe you'll find traction on that. All right, so that's all I've got. I hope this helps. Projectile motion example problem, and I'll see you later.